Permutations and combinations.
Yeah.
Okay.
Stop all the little side conversations now. We're doing. Okay. So a permutation, you know what that is, right? It's a cat with 5 legs. It's a permutation. Okay, that was my joke of the day. So we're going to talk about permutations and combinations. A permutation is usually it's a ordered arrangement of objects, and the word ordered is important with permutation. With a combination, those things are not in order. So Ryan, who just went to Chipotle,
That's me.
right? So part of the reason Chipotle, I think, is so successful is because they have a limited amount of stuff, but they have lots of ways you can order it, right? So like, and I'm going to keep it kind of simple here. So say, for example, oh, I need my sample space. Wait, where'd my sample space? Here it goes. I could hide this. Where's this? So say, for example, that I go to Chipotle and I choose, how many different types of meat can you choose at Chipotle?
It's like 5. 4.
4. I
There's
think.
4 meat business and veggies.
Okay, let's not just have you can have the barbecue, right? Or you could have the chicken, right? Or you could have the steak, right? Or you could have the, isn't that?
That's the
What
barbecue.
carnitas?
So barbacoa is pork and shredded beef is different.
Okay, whatever, okay? So I think there's 4 different choices, right? Then, for beans, say you're just gonna get a rice, bean, and cheese and salsa burrito. How many different types of, 2, right? You can either have black beans, or you can have pinto beans. And then, for rice,
White or brown?
yep, now they have 2 choices of rice. You can have white or brown, okay? And then how about salsas?
There's 3 types. No, there's 4.
There's 4, right? There's like the corn stuff, right?
There's
And
cheese
then
on it.
Corn, mild,
and there's the mild, then there's the green, and then there's the caliente. Yeah. I think that's that one, pico de gallo.
No, pico de gallo is mountain.
That's another one?
Yeah.
So then you
No,
can get
pico de
it.
gallo is a mild one.
Yeah. Yeah, pico,
I was
okay.
just thinking
In any case, so to figure out just with these things, and then you have the choice of with cheese, without cheese, with the lettuce, guacamole, sour cream, all that kind of stuff. But just with these choices, how many different burritos can I make? Anyone know? It would be 4 times 2 times 2 times 4, which comes out to be 64 different burritos you could have just with those 4 things. And the reason for that, Mena, is because you could represent that by having like a tree diagram. So if I were to choose barbacoa, for instance, I could either choose barbacoa with black beans or pinto beans, right? And then if I choose barbacoa with pinto beans, then I could choose white rice or brown rice. And then if I choose barbacoa with pinto beans and brown rice,
Choose white rice.
brown rice, and then I get 4 choices for this. See that? Okay? So here is like one choice you can make: barbacoa with pinto beans, brown rice, and mild sauce. Okay? So altogether, you would have 4 times 2 times 2 times 4, which is 64 different combinations, right? So with a very limited amount of ingredients, they can have a whole bunch of different combinations, and that's part of the reason they're probably so successful, is because they don't have to, they're never running out of this and never that, and stuff like that. And they keep it pretty simple, and they charge pretty much for their burritos, and they taste other choice that you could add in there, like not getting this or not getting that. But, so, that takes you back to the multiplication principle, which says that, okay, which is this right here. Multiplication principle of counting. If a task consists of a sequence of choices in which there are p selections for the first choice, q selections for the second choice, r selections for the third choice, and so on, then the task of making these selections can be done in p times q times r ways. Okay? So, how many three-course dinners could you have? So in this case, there's how many choices for this? There's 2 choices, 4 choices, 3, and 3 choices. So 2 times 4 times 3, which is 24. Okay? So, you get that? And that's the way that works. Now, Colorado license plates, 1958. Colorado license plates contain 2 letters and 3 numbers. How many license plates were created? So the way you can think about this, anyone tell me? There's 20, where do you get 27 from? Yeah, so it'd be 26 times 26 times 10 times 10 times 10. 0. Why 10? Okay? Because there's 26 choices for the first letter, right? 26 choices for the second letter, and 10 choices for each number. I think you could put a 0 in there. Yeah. So how many, if there were no repetition of letters or numbers, how would that change? Wait, I have someone coming to bug me right now.
Did I leave my box in here?
Did you leave
Does
her
it
box?
look like it?
No, it's small and okay.
You guys are very small. So, if there's no repetition of letters, you still have 26 for this, right? And 25 for that. How many choices for this? 10. And you're not allowed to repeat times 9 times 8, okay? And if you multiply this out, what's 26 times 26? I have that in the last. Anyone have a calculator handy? 676? So this is going to be 676, 000, okay? So that's, that's how many different license plates you could have if this were your license plate. Now, probably nowadays, that's a problem because there's probably, I don't know what the population of Colorado is, but it's probably well over 1 million, right? And so what they have to do is they made new license plates where you have 3 letters, right? 26 times 26 times 26 times, and 3 numbers, right?
And then the thing is, you can also customize it.
Yeah, you could customize, but you're not allowed to spell like bad words and stuff. So they have the people at the license plate factory, who are usually, a lot of times those are inmates. They make license plates.
Really?
Yeah, that's what they have them do.
Seems like the
Okay,
inmates would follow those.
but, well, someone screens them to make sure there's no bad words allowed, you know. And then there's certain letters, like, I'm not sure, but certain letters. Anyway. Okay. So, moving on, guys. So, how many different arrangements of the letters in A, B, C, and D are possible? Okay. So, what? No. 4 times 3 times 2. So, if it's like this, okay, there's 4 different letters, so you would have 4 choices for the first, 3 for the second, 2 times there, and 1, which is 4 times 3 times 2 times 1, which is 24, aka 4 factorial, right? You understand that? Okay? Because you have 4, say you were putting these, right, somewhere. So you could have A in the first spot. So if you chose A in the first spot, then I have three possibilities for the second spot, right? B, C, or D, right? And if you chose B in the first spot, then you'd have, right? Yeah, and then over here, if you chose B, then you'd have two choices for the third spot and one more choice. So altogether, you get 4 times 3 times 2 times 1, which is 24.
If you could repeat those letters, it would be 4 times 4 times 4 times 4.
Yeah, you could repeat them, but these are all the things you have, so you just have those 4 there. No, I think that's, you have to use all 4 of those letters, okay? So you have to use each letter once. So for instance, if you have 5 people in a lineup, how many different lineups could you have? How many different lineups? Yes?
24 times 5.
Right. 24 times 4, 5 times 4 times 3 times 2 times 1, or 5 factorial, or 120, right? Now, so these 7p73, okay, a permutation is a little bit different. It's different than a combination. With a permutation, it's defined as np. Or you write it like this. There's a button on your calculator near the combination button. NBR means n factorial over n minus r factorial. Okay? And what this kind of means, 7, so what it means kind of in real life, you have 7 things and you're putting them in 3 spots. Okay? So 7 times 7 permutation 3, which is how you would read that. Sometimes they write it like this, P73, and most of the time they write it like this, 7P3, like that means the same thing. Means you have 7 choices for this item, 6 choices for that item, and or for this spot, and 5 choices for that spot. Okay, so 7P3 would be 7 times 6 times 5, which is 42 times 5, which is 200 and something. 42 times 5? 210. 210. Thank you, Dan. Okay?
Where'd you get that?
7 times 6 times 5.
You have to
Okay?
number it as 0.
What? Yeah, you have to number it at a 0. Oh, I didn't know that. Okay? Or using this formula, which is somewhat more complicated, you can think of this as n factorial, so it'd be 7 times 6 times 5. I'm going to stop there and write that as 5 factorial. What's n minus r factorial? Since r is 3, 7 minus 3 is, whoops, I should have gone one more spot. 7 times 5 times 4 factorial, okay, over 4 factorial. And then you can cancel those out like that. So that's another way to look at it. So it's this factorial over this minus this factorial. So 6 permutation 1 means 6 things in one spot to put them in. So how many choices do I have for that one spot? 6. It's just 6, right? Or you can think of that as 6 factorial over 6 minus 1 factorial, which is 5 factorial, and if you wrote this out, the top, you could write that as 6 times 5 factorial over 5 factorial, and you could cancel those out like that, okay? And so 52 factorial would just be 52 times 51 times 50 times 49 times 48. Yes?
Yeah.
See? Okay. So that's that. Now, how many distinguishable arrangements of the letters in the word banana are possible? Okay. No, you would think that it would be 6 factorial.
3
But
factorial.
there's repeating letters.
There's repeating, yes, that matters. Okay. So, very good, Amanda.
But aren't there always going to be 6 spaces?
Watch. So, say I'm arranging these letters, Okay, one, how many letters are there? 6 or 7? 1, 2, 6. 1, 2, 3, 4, 5, 6. How many letters can I choose to put in here? 6. If I choose one, then I have 5 for here, 4 for here, 3 for here, 2 for here, and 1 for there, right? However, say I have one of my A's is over here, okay? I'm going to call this A sub 1, okay? And say another one of my A's is here. I'm going to call this A sub 2. And let's say another one of my A's is over here, 3. How many ways are there to arrange those A's?
1.
Very good, Jack. There's 6 ways to arrange those A's, right? Because you could have A1 here, then A3 and A2. You could have A2 here, and then A1 and A3, A2 here and A3 and A1, and so on. So there are 6 or 3 factorial ways to arrange those A's. So I have to divide by 3 factorial. And how many ways are there to arrange these n's?
2.
There's 2 ways to arrange the n's, right? So say my n's are here. So here's one n, and here's another n. Let's just, because I'm already accounting for the different positions by doing this 6 times 5 times 4 times 3 times 2 times 1. That's if every letter was different, right? But since these n's, they're indistinguishable, whether this n is here, this n is here, or vice versa, there's 2 ways to arrange those n's. For each spot, those n's could be in, right? And so I also have to divide by 2 factorial, okay? And so when you have repeated letters, okay, you have to divide by the factorial of the number of times that letter repeats. For example, say you have the word Mississippi. Tell me if I spelled this wrong. I think that's how you spell it.
That's right.
Mississippi. Thank you. How many arrangements of letters, not that they would all spell words, would there be in Mississippi? What would I start with on the top? 11 letters, but then I'd have to divide by how many S's are there?
4.
4 factorial, and there's 4 factorial I's, right? And 2 factorial P's, and then you don't have to worry about the M's because there's just one of those. See? Okay, so you would divide by. So there's a formula in your book that says if to tell when there's repeated items, then you have to divide by the number of times that thing, the factorial of the number of times that that thing repeats. It looks like this. And for arrangements, to find out how many distinguishable arrangements there are when you have repeated items, it's n factorial over n sub 1, I think they do it f sub 1 factorial, times n sub 2 factorial, n sub 3 factorial, dot, 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 dot. And each one of these represents one of these letters, okay, that's being repeated, and how many times each one of these things is being repeated. Okay. Anyway, so that's permutations. We could do that. This one, here we have Isabella, even Amanda. How many different ways could they have their birthdays if they can't have their birthday on the same day? How would I do that? 365 choices for the first spot. 364 times 363. Okay? But unfortunately, now we have combinations. Okay? And combinations are more interesting. So a combination lock, you know combination locks? Those aren't really combination locks. Those are really permutation locks. That's what they should be called. Because does order matter when you're doing a combination? Yes, a combination lock. But with a combination, C for combination 2 over here, the order does not matter. So if list all the combinations of 4 objects, A, B, C, D, taken 2 at a time. What that means is you have 2 spots, okay? And you need to put 4 things in those 2 spots. So what's one possibility? A, B, okay? Now, if I switch these and it says taken two at a time, that implies that it doesn't matter what the order is, okay? So you're choosing a president and a vice president. No, that's not a good one. You're choosing two people for the,
Two different types of candies from a bag that you're gonna eat the most.
there are two people for a committee from 4 people, okay? And so it doesn't matter which order those people go in, okay? So is AB the same as BA?
Yes.
Yeah.
So in this case, what I'd have is 4 choices for the first thing, and how many choices would I have for the second thing? 3. But then I would have to divide by the number of arrangements of 2 items. So 4, what do I have to divide by? 2. I'd have to divide that by 2 factorial, okay, or 2 ways. So if I have 3 items, then I have to arrange that, divide that by 3 factorial. And that's what a combination is, okay? So for example, before I jump to these, okay, say I want to choose how many different 3-person committees can you get from a pool of 7 people? So 1, 2, 3. How many choices for here? 7. How many choices for here? 6. How many choices for here? 5. Okay. So say my people are Fred, Ethel, and Wilma. No, what's Barney's wife? Fred, Wilma, and what's Barney's wife's name?
Wow.
Betty. Fred, Betty, and Wilma, right? So if I do this 7, 6, 5, and the people I choose for my committee are Fred, Betty, and Wilma, then Wilma, Betty, and Fred, right? That's considered another set of people, right? But in this case, it doesn't matter. So I have to divide by the number of arrangements. There's also Betty, Fred, Wilma, right? There's also Fred, Betty, Wilma, etc. So what I have to do is divide that by 3 factorial, okay?
Why? Can you explain why again?
Okay? Because out of any 3 objects that I choose from those 7, right, there are 3 factorial ways to arrange them, okay? So again, I could have Fred, Betty, Wilma. I could have Fred, Wilma, Betty, right? I could have Wilma, Betty, Fred. I could have Wilma, Fred, Betty, right? I could have Betty, Fred, Wilma, and I could have Betty, Wilma, Fred. Those are my 6. Yes?
But you said the order doesn't matter.
That's right. So when I do this, the order does matter. So I'm considering, in this case, I'm considering Fred, Betty, Wilma, and Fred, Wilma, Betty to be 2 different arrangements, okay? But when it doesn't matter, I need to divide away those different arrangements, okay? So I'm going to divide away my 6 different ways. So I'm going to divide by 3 factorial. And that's what a combination is. So this can be written as 7 combination 3, okay? And the way mathematically they define a combination, which we talked about when we talked about binomial theorem, is n combination r, okay, is equal to n factorial over n minus r factorial. This is just if it were a permutation, times r factorial on the bottom. So what you have to do, is a combination going to be more or less than a permutation?
Permutation would be more.
There's way more in a permutation than in a combination, right? Because in a combination you have to divide out all the repeats, okay? So like if you're choosing card hands, how many different 5-card hands could you have? No, 52 combination 5, right? Because it doesn't matter whether you go ace, king, jack, whatever, versus, right? It doesn't matter what order those cards are in, right? When you get them. So when you're choosing cards hand, that's how many different 5-card hands you could be dealt when you're playing.
So
So it'd be like 52, it'd be 52, 50,
Maybe
51.
52 times 51 times 50 times 49 times 48 divided by 5 factorial. Okay? That's what that would look like. So that's how many different card hands you could have, which is like, if someone can figure that out, you could do that on your calculator. Let's do it on our calculator. Okay? So your calculator will do stuff like that for you. So if you go to here, did I go to there?
I've got it, Mr.
Let me just do it. So I can show people. Come on, there we go.
You know, we get 6.72
So-
times 10 to the 64.
No, that's too big, okay? It's just 52, then you go to math, and then you go over here to PRB. So if you want the permutation, that's there. If you want the combination, you go there. So I'm going to go down to 52. First I type in 52, then I go to that button, and then I hit 5. And so what I get for how many different card hands could you have in a game of 5-card poker? You'd have 2,598,960 different combinations. So when we get into probabilities, what do you think the probability of getting a 2 of a kind is? It's pretty high. And I just want to show you, this isn't this part yet, but on the bottom, you get your total number of combinations. So there's your 2,598,960. But then on the top, I can choose, you have 4 cards to choose from, and how many, if you're getting 2 of a kind, it's 4 combination 2. You understand that? But then, I have 3 other spots. How many ways do I have to choose those 3 other spots? 50, because I've taken 2 cards. Now I have 50 left, right? And these cards could be anything else. So you have 50 times 49 times 48. See, probability can get kind of complicated. But so these are the ways to arrange 2 cards. But, oh, I forgot something. How many different ways could you get 2 of a kind? How many different, what denominations are there? No. There's 1, 2, 3, 4, 5, 6, 7, 8, 13. Okay? So you can, this is the total number of 2 combinations of 2 or more of the same kind. Because it's 13 times 4 combination 2 times 50 times 49 is 48. You want to figure out the probability of that, you divide by that. And that comes out to be about 0.4 something. Okay? And so you have about a 40% chance of getting 2 of a kind. If you go to 3 of a kind, right, then this number changes to 4 combination 3, and then you just have times 49 and 48. See, but there's lots of complications, and then you have full houses, and it gets hard. We're not going to do that too much card probability, but a little bit.
Wait, Mr. Lee.
What?
Where do you get 4 from?
We're not, because that's like, say you have 10s, right? So you have 4 different 10s to choose from,
yeah.
right?
Okay.
And so you say this is a 10 of clubs and the 10 of diamonds,
Yeah.
right? So the 2 would have gone here because you could choose a 10 of clubs, 10 of diamonds, or the 10 of diamonds, 10 of clubs. But the 13, because that could be a 9, or an 8, or a 7, or a 6, or an ace, or a king, or queen, okay? And so on. So anyway, that's it. So 2 more problems, then I'll be done, and then you guys can go
To bed.
to bed. There you go. So so this way, this is so 3 combination 1, that just comes out to be, anyone? That's just 3. And you can think about it using the formula, or you can just think about it, you have 1 spot and you have 3 things to put in it, right? So this means 6 combination 3. So you have 3 spots and 6 things you could put in there, okay? But then I have to divide that by 3 factorial, right? So 3 factorial is 6. So that would be 20, right? You understand that? If you, because 3, why what?
Why is it 120?
Why is it 120?
Yeah, why do you?
Because it's 5, because it's 6 choices for here, 5 choices for here, 4 choices for here. But there's 3 factorial ways to arrange each of those choices. They have to divide away 3 factorial. And 3 factorial is 3 times 2, which is 6. So I can divide that away. Okay? N choose n is always equal to 1. Because that's like, okay? And n choose 0 is also always equal to 1. Okay? And then if you have a problem like this, let me just go real quick.
Just really you're not doing anything combination 0 to 1, you have 0 spots.
That's just by definition, so it works.
It's by definition.
It's by, this one actually makes sense. This one is just by definition, so the math works. Okay? Hey, a couple more minutes. So in how many different ways can a committee consisting of 2 faculty members, 3 students be formed if 6 faculty members and 10 students are eligible to serve on the committee? So you have 6 faculty members, so it's 6 combination 2 times 10 students, 10 combination, how many are you choosing? 3. And if you just multiply those 2 things together, you would get the number of different committees. Okay? Do you understand that? So that would be 6 times 5 divided by 2 times 10 times 9 times 8 divided by 3 factorial. Okay? And you can compute that pretty quickly by hand. That's 15, right? 15. So that's 15. And this is 3 times 2, and you can cancel things out, make it work. How many different vertical arrangements are there? Like, so for this one, 8 flags. 8 flags. 8 flags, 4 white, 3 are blue, and 1 are red. So this is just like the Mississippi problem, but I want to show you a different way to think about it, okay? So let me draw, make a bigger picture. Yeah, right, that's no good. I gotta go back. So 2 ways to think about this, okay? You can think of this as 8 factorial over 4 factorial, 3 factorial, 1 factorial if you want it, because there's 8 different things. What?
Say 1 factorial is
1 factorial is just 1. So you have 8 flags, 4 are white, 3 are blue, 1 is red. Or you can think of this as 8 combination. I'm going to pick 4 things. Once I have chosen that 4 things, how many do I have left to choose? So I have 8 spots. 1, 2, 3, 4, 5, 6, 7, 8. Once I've got rid of 4 spots, how many are left? 4. And in those 4 spots, 3 of them are going to be reserved for blue things. Okay? Times, then the last spot, once I've got rid of those, the last spot is there's 1 red flag. Okay? So if I do this or this, I get the same answer. I could show you that that's true. 8 times 7 times 6 times 5 times 4 factorial over 4 factorial times 3 factorial, right? Wait, 8 times 7 times 6 times 5 times 4, and this cancels out, right? And the 3, this cancels out with this, and I get 8 times 7 times 5. Over here, this is 8 times 7 times 6 times 5 times 4 factorial over 4 factorial times 4 factorial, right? Because it's 8, it's P minus R times R times 4 times 3 times 2 times 1 over 1 factorial times 1 factorial. And this cancels with this. And then I think, whoops, did I forget a 3 factorial somewhere? Whoops, I forgot a 3 factorial over here. 3 factorial. And I get the same thing, right? 8 times 7 times 6 times 5 over 4 factorial, 3 factorial. And this cancels with this. And this cancels with 4 times 3 times 2. That cancels with 4 times 3 times 2. I get 8 times 7 times 6 times 5, which is the same as what I ended up with over here. Anyway, so your homework's on that sheet. We're gonna stop. Because
We're tired.
you're tired.
We're tired.
You're tired.
Yes.